Welcome everyone. This is Khalil. I'm a PhD student from the Computer Science Department of the University of Alabama at Birmingham. Today I will give a presentation on realistic transport simulation for studying the impacts of shared micromobility services. Shared micromobility services see increasing deployment in urban areas. A key question to ask: how much car traffic can be reduced during peak hours if this service is deployed? This work answers this question by agent-based transportation simulation. As we can see in this video, this is the simulation result showing cars and e-scooters traveling around the city of Birmingham, Alabama. More specifically, around the University of Alabama at Birmingham, UAB. We choose the campus of UAB as the target area to study, since UAB is a functional zone for education, research, and healthcare. We surveyed both students and employees in our case study. For this purpose, we conducted a mobility survey of UAB students and employees, which was used to obtain the location distributions of their homes, apartments, and workplaces. There are two challenges indirectly using the survey data. First, to protect the privacy of the participants, the exact locations, for example building numbers, are not disclosed, but rather in the form of nearest intersection with zip code and city, as we can see in the tables. Second, the survey only includes a certain portion of all UAB employees and students, but the simulation requires the day plans of an entire population. In the next slides, we will see how we tackle these challenges. We need different types of data in order to create agent daily plans that we will use in the simulation. We have to find the following: home locations for students and employees, work locations, parking locations, classrooms, and e-scooter stations. In the next slides, we will discuss these types of data in details. Let's start with the student home locations. Recall that we have information about students' daily trips from the survey. The first challenge that this information is not exact to protect participants' privacy. So we use these data with an address geocoding API to get an approximate locations. We separated the approximate home locations into two sets: off-campus set that we see in red and on-campus set that we see in green. In order to decide if a location is on campus, we used UAB campus polygon that we got from OpenStreetMap. The second challenge, that the survey only includes a certain portion of all UAB employees and students. So we used a kernel density estimation, KDE, to fit the 2D location distribution. We created two KDE models using the approximate home locations, one for on-campus and the other for off-campus, so we can sample new home locations on demand. However, sampled home locations may not correspond to an actual home or apartment location. For example, we can see some sampled on-campus locations on streets. For this purpose, we collected data on the locations of apartments inside and around the city of Birmingham from online sources such as apartments.com, rent.com, and others, and we collected on-campus apartments from UAB official website. Then, we need to align the sampled location to a nearby apartment or address location for realistic simulation. For example, in case of a campus apartments, we first align the sampled location to a random apartment within a radius of 300 meters. If we cannot find such an apartment, we then sample a random on-campus apartment. Same for off-campus apartments, with one difference, that we sample a random address from Open Addresses home location within 300 meters. For classes and classroom details, we used UAB class schedule to obtain the class information of a particular day for simulation purpose. The day we choose is Wednesday in fall 2020, which is before remote teaching due to the COVID-19 pandemic. We used the building code column to find the exact classroom locations. Also, we used class entry time and class exit time in the plan generation process, as we will see later. For the parking locations, We obtain the data from UAB Transportation Department, where each parking location has information including the parking type, address, and parking capacity. Then we use the geocoding API to get to the exact location. As an example, we can see a student drive first to a parking location, then he or she is walking to the class. One question to answer: which parking location to choose? Intuitively, students would prefer parking locations closer to their classrooms. We proposed a scoring function depend on the distance between home location and all parking locations, also the distance between parking locations and classes, to decide the score of each parking location. How the score function is working? We assign the preference score to each parking location based on two distances. First, the distance between home and each parking location denoted by DHP. Second, the distance between each parking location and the class denoted by DPC, where alpha balances the importance of both distances. We have one problem, that the distance between home and parking location is usually much longer than the distance between parking location and class. So, the first term in the equation is overrated. To avoid this issue, we deduct from DHP a constant distance denoted by DHUAB that the students must travel anyway, no matter which on-campus location he or she arrives. Now that we have scores for all parking locations, we sort the parking locations in a non-decreasing order to obtain the preference list. However, in busy hours, where many classes are ongoing, the parking locations nearby a classroom may be full, forcing students to find a farther away parking location with available space. As a result, we use a Poisson distribution to determine if a parking location has a space by answering the following question. What is the probability of finding that the number of vehicles in a parking location right before the class time is less than parking capacity? Now, if we look to the sorted scores and the capacity of each parking location, we can easily decide the best parking location. Next, we will discuss the plan generation part. We are using an agent-based transportation simulation software called MATSim to run traffic simulation. MATSim takes the travel day plans of a population and executes them on the underlying road network to generate simulated traffic. The execution runs the selected plans in the synthetic road network environment. Then, MATSim scoring function assigns a score to each plan, based on the corresponding agent's experiences with the selected day plans. Afterwards, the replanning step selects a candidate plan based on the plan scores in each agent's day plan pool, and may modify this plan for execution in the next iteration. 3 files are required to run MATSim. The config file contains the configuration parameters that may be modified or tuned. The network file contains the nodes and the links that makes the network. We used OpenStreetMap to get the network file. MATSim also requires a file named plans.xml, containing the day plans of each agent or traveler to run a simulation job. So, the key to a successful simulation is to generate realistic population day plans in the simulation area. Each plan has different activities and modes. Each activity contains information about its location, start and end time. The mode determines the transportation mode between activities, such as walking, driving, or using e-scooter. Our goal is to use all the previous data sources to prepare the plans.xml file. MATSim does not have an extended module that directly supports e-scooters for shared micromobility simulation. The closest module to our need is MATSim car sharing module. So, we revised MATSim car sharing module to support multiple types of shared micromobility modes, including e-scooters that we need. Each shared mobility mode needs to specify a few attributes for proper simulation by MATSim, such as maximum speed, passenger car unit, length, and width. MATSim's subtour mode choice strategy that used for planning was enabled, so that MATSim can try different modes such as car, walk, or e-scooter. This means that the best plan, using e-scooters or not, can be selected due to its better score. We consider three types of traffic that constitute the majority of UAB traffic. Background traffic, where travelers are just passing through UAB, which is neither origin nor destination. Traffic generated by students attending classes. And traffic generated by employees going to work. In a previous research paper, we have generated a transportation simulation for the entire city of Birmingham with the help of a small seed mobility survey. We partitioned the city into zip codes and determined the number of trips between each origin and destination. We used different types of real-life activities such as work, school, shopping, and others. As a result, we built an origin-destination matrix showing number of people moving from one zip code to another. We adopted the three types of student plans. Students who are walking to the classroom, either they are living on campus or living off campus but very close. Students who live off campus and drive to a parking location, then walk to the classroom. And students who live off campus and drive to the classroom, so they use the roadside parking. Employee plans are similar, where we also adopted the three types of plans. Employees driving a car to the work location. Employees driving a car to a parking location first, then walking to the work location. And employees walking directly to the work location. Now, we will discuss the time sampling process. Let's start with the home to class plan. Since we already know the class start and end time, we will use these details to generate other times. To generate a realistic leaving home time for a student plan, we need to make sure that the student is able to arrive at the classroom before the class begins time. In particular, we need to count the travel time home to class and an additional amount of time T1 describing how much earlier a student typically tends to arrive at the classroom. To ensure the diversity of classroom arrival time by different students, we sample T1 from normal distribution. We also need to generate the leaving class time and the back home time. In reality, students do not leave before a class ends, and many students leave the classroom a few minutes after the class end time. We denote the length of the time from when class ends to when a student leaves the classroom by T2, and to impose diversity, we sample T2 from an exponential distribution. Since the working hours for employees are unknown, so we sample the arrival time at the workplace randomly from 8 to 10 a.m. using the uniform distribution, and sample the departure time randomly from 4 p.m. to 6 p.m., since most UAB employees commute during peak hours. In the case of parking locations, we still use the same calculations, but we include the parking location. So we first find the distance between home and parking location, then the distance between parking location and the class. We conducted our simulation using 500 e-scooters to match the number recently deployed by a company named Vio as a part of the Birmingham Micromobility pilot program. We used a total of 22,000 students, depending on the number of students attending classes, and a total of 20,000 employees, which is comparable to the number reported by Birmingham Business Alliance. We measured the hourly volume and average speed on two major road segments at the center of UAB, where many classroom buildings are located. They are the 14th Street South and the University Boulevard. To explore how much traffic can be reduced in the presence of e-scooters, we also ran another simulation without the option of e-scooter, and we call it the baseline. The diagram shows that using e-scooters clearly reduces the car traffic volume in almost all hours. Regarding the speed, our results prove that allowing e-scooters generally increase the speed, especially during peak hours, indicating that traffic flow is improved when using e-scooter mode, which reduces congestion. We can visualize the traffic simulation around UAB at different hours. Triangle icons represent cars, where the colors mean different speeds. For example, a red triangle means a slow vehicle. We also can see the bicycle icons that are used to represent e-scooters. Let's see the traffic at 7 a.m., where we can see some e-scooters around the UAB campus. If we try a time at afternoon, we can see clearly congestion around the UAB campus. This happens because the students are heading to or leaving classrooms at that time range. Thank you so much for your interest and attention.